Well, welcome everybody to the ISSA Tuesday, June 9th meeting. This is on RF Hacking 101, Signal Analysis and Replay Attacks. Couple of minor housekeeping things. We will be having another meeting on Thursday at this time, so take a look, log on and register. It'll be an interesting meeting. Also, for those who might have questions or comments, we take all of our questions and comments from the ISSA Denver Slack channel, the ISSA_Denver channel, as a matter of fact. Type your questions and your comments in there, and then near the end of the presentation, I'll take a look at them, and we'll go ahead and ask them then. So with that, I'll introduce our speaker for today, Priyank Nigam. He's and I really hope I pronounced that right. He is a senior security engineer, and his primary focus is web and mobile application penetration testing. I don't understand that. Of course, our phones are completely secure, so there shouldn't be any worries there. Any rate, over the past 5 years, he's advised Fortune 500 brands and startups, and does a lot of mobile and, that infamous 3-letter acronym IoT-related research. With that, a little bit about it. I'm sure we're all familiar with RF-based systems. They're pretty much everywhere. You walk into, department stores or bookstores, wireless doorbells, home security systems. I mean, you name it. And he is going to give an applied tutorial on how to reverse engineer some of these unknown radio-based frequency protocols, and how to do replay attacks, all that sort of good stuff. He'll of course start with a little crash course on digital radio fundamentals for those of us that don't do that as a full-time job. And with that, I will turn it over to Priyank.
Thanks, Greg. Thanks for the introduction. And thanks, Scott and Joe, for supporting this. Am I audible, right?
Yep, just fine.
Perfect. Okay. So this is like a short brain dump on RF hacking, which I was doing a little while ago. And we'll focus mainly on RF signal analysis and replay attacks. For this purpose, is also have like a wireless doorbell. It's like a general line which you find on retail shops, So I'll do a short demo in the end. We'll briefly touch base on SDR equipment as well, but think about this as a lecture on how to reverse engineer the signal. Most of this can and already has been automated, but knowing the fundamentals, there are like tools out there which will actually help you decode the signal and go out there from there. So yeah, if the quality is bad or something, hit me up after this talk. This is being recorded. This is going to go up on the Bishop Fox YouTube channel as well as the ISSA Denver YouTube account. So with that, let's get started. So a little bit about me. I'm a senior consultant at Bishop Fox. We are a shop which basically do offensive security for all kind of stuff in all domains, and that's primarily what my interest is. And everything offensive, name it, web, mobile, wireless, IoT, and for some nonsense output, that's my Twitter handle right there. So you can follow me for more updates. So this is the roadmap we're going to be following. We're going to hit the basics. We're going to look at what hardware is good and bad. We'll jump on to the RE process of analysis. Then we're going to look at the demo of how all of this tie in together and work together. So yeah. So So RF, basically radio frequencies, these are omnipresent. When we talk about RF waves, so you just name it. It's like cell phones, wireless devices, airplanes, all these home security systems, in and out, and even in the industrial world, So that's the reason we should be interested in this, because not all of these systems have the security in mind. They were not designed with that. They were designed with communication in mind. But now it's becoming so easier to understand them. You have like cheap hardware available in the market, which will help you decode these, and depending on the application, you can do unintended things. So yeah, it's pretty much interesting, and that's the reason we'll focus on the fundamentals first. So when we talk about RF waves, there are two main ways to describe them. The one is wavelength, the other is frequency. So wavelength is basically the distance between the peaks of two waves. So now this is like a representation. There's no actual peak, but that actually represents an amplitude of the wave. So an amplitude is controlled by the power which you give on the radio transmitter. So the higher the power, the higher the amplitude goes. And the rate at which you vary that power is basically the frequency. So if you look at the graph, which is like basically a Fourier transform it's a representation on paper. So you're going to see the more number of peaks in 1 second, the higher the frequency. So, and that's how you describe the waves, and like long wavelength, short wavelength, high frequency, high energy, stuff like that. So yeah. And then there's other concepts of modulation, which is basically how are we going to add information to these radio waves, because we want to communicate over these radio, right? So the way you have to vary certain aspects of the wave in order for you to, the receiver to make sense of it. And of course, this has to be agreed between the transmitter and receiver beforehand. So there are like these are the main types of modulation, and that is called modulation, actually. Sorry, I didn't mention that. So these are the types of analog modulation, and then we'll talk about digital ones. So the first one is like very common, which we are going to use in this demo as well, is the on-off keying, which basically is if the signal is on, the transmitter is transmitting, it would represent something. So for example, in digital wave, it would be like a 1, and 0 would be represented by nothing. So it's like on and off, on and off. So if you have something like a Morse code or those kind of systems, this is what the modulation will be using it. And then there are like the AM, amplitude modulation, which again, as we talked about, the amplitude is a function of the power of the transmitter. So if you can vary that, you're gonna get a spectrum. You're gonna see a representation like in this diagram where you're varying the amplitude, and you can decode that and make sense of the information. So it's, the AM radio, you see, or I think older analog TV signals also use this kind of modulation. Next one is frequency modulation. It basically changes the frequency and how many waves are passed per second to carry this information. So yeah, the most common thing which comes to our mind is FM radio. And then the last one is phase modulation, which is basically used in applications. And so basically this is related to FM, but the relationship is not linear. So you're not directly varying as a relation of the frequency, but as a relation to the phase of the wave. It's just an indirect way of producing an FM. If you look at it, it's kind of very difficult to distinguish between PM and FM. But yeah. So let's talk about digital modulation. And so these are the signals which we are interested from a security point of view, because everything nowadays is digital. So it has to be like ones and zeros. So if you see something like this on a captured waveform, it's going to likely represent ones and zeros. So our job is to figure out what these mean. How well can we decode that pattern, and then it will help us understand what's going on there. So the first one is ASK. So it's like an amplitude shift keying, which looks very similar to the on-off keying in the analog phase. But yeah, it's the same thing. You vary, if the amplitude is high, power is high, it's going to represent 1. And then you can figure out, if depending on the duration of how long it works for, you can see like if they're like a series of 1s or series of 0s and further. Next is frequency shift. So the pulse is represented. So you kind of typically they choose like 2 frequencies. It's also called 2FSK though, where you and like, hey, let's say 300 megahertz represents 1, whereas 315 would represent a 0, and and you vary between those 2 frequencies. So that's how the receiver can decode to what's going on there. So that's FSK. And then PSK is phase shift keying. You vary the phase related to that wave, and the receiver can decode that. So ARF bands, we don't need to go much into detail about this, but this is basically the whole spectrum of RF. So you could start with like very low frequency, so there's an interesting relation between frequency and wavelength, whereas they are inversely proportional to each other. So if you have very low frequency, the range would be very high, and vice versa. So if you look at the low frequency waves, they are mostly used in navigational systems because you need to traverse like really long distances, and then on the other extreme, it's like the high frequency, but the range would be very short. So for example, if you think, let's say like a 5 gigahertz wireless, the range would be very short, but the signal will be very strong, and vice versa, as compared to a 2.4 gigahertz wireless, where it would be like a little long. So yeah, we will be focusing mostly on the ISM band, which is basically, so most of these bands are actually reserved. They are regulated, but there are certain bands which are not, and those are used for like industrial, scientific, and medical purposes. This is the ISM band. So the very high frequency and the ultra high frequency, those are the interesting bands where most of these home devices or even industrial devices work on. So for example, I think in EU region, it's mostly 433 megahertz for most RF-based systems. Think like key fobs and like motion sensors and stuff like that. In the US, I think it's 3. Not just US, it's like in the rest of the world actually. It's like 315 megahertz. So yeah, a lot of our modern devices operate on that, like Wi-Fi, Bluetooth, microwave, 4G, even drones. That's how they communicate in this range. So with that, let's get talking about the hardware. So there are like too many hardware out there, and especially with SDR equipment becoming more popular, there are more and more options. So I'm going to focus on a not too expensive one, hardware with respect to the stock. But actually, in general, the more expensive the hardware is, the easier it is to use, because you have more software support, and as well as more firmware support. So it's just easier. Like, you might have like something for like a Python bindings for accessing the same thing, or similar like that. So so this RTLSDR, this is the most common one out there. It's pretty cheap. It's like 25 bucks. So the only downside is that the frequency is very limited. It can only receive frequencies from 500 to 1.5 gigahertz. It's one way only, it's receive only. So that's like a half duplex communication. And also it has a very small sample rate. So if you are sending data like really high, change of data, this probably isn't a good fit there. But for this purposes of this demo, it's going to be like a really handy device. And then most software for this is community developed. So you have RTLSDR software for Linux, for Windows, under different names, for Mac OS as well. So it's pretty accessible. Anyone can get started with RTLSDR. You can even use this, just to listen to FM radio or AM radio, or there are like a lot of information going on, like weather information, highway patrol, etc. You can literally snoop on using these. And then the second piece of hardware which I'm using is this is like a simple transceiver. It's called Yardstick 1. So this is like really great for transmitting and receiving RF at frequencies below 1 gigahertz. So one of the drawbacks is this half duplex transmit or receive, meaning that it can only either transmit or receive at a single point in time. So these are the official frequencies, but I know you can fine tune it to even go up a little more above 1 gigahertz or something, but it starts at 300. And then you have to exclude some of them because some frequencies are actually regulated. So there are other SDR options as well. But these automate a lot of RE work, which we are going to be discussing. But again, you're not going to learn anything from it because, for example, these all are like $100+ devices. So you can record a signal literally, and you can replay it, and it's gonna work, because the firmware handles everything of this. But you see, there's no end to it because you can also use like a very cheap device like an Arduino with their RF transmitter. It would just really work fine, but it would require a little bit of more programming. But then the concepts are all the same. It's literally the same. So yeah, that's about it for hardware. I don't think we need much from there. Let's move on to signal analysis. And this is the workflow we're going to be following, wherein we find the signal, we record it, and then we analyze it. And the goal is to identify these attributes of the signal. So these are the main ones, like frequency, which we discussed, bandwidth, which is how wide the signal is basically when it comes to the frequency domain. The modulation and the symbol rate. Modulation is just how the information is being transferred, ESK or FSK or something like that. Symbol rate is the rate of how many bits per second is being transmitted. What is the rate of encoding we're doing on the wave? It's also called baud rate sometimes. And then we have the packet structure elements, which is, then this is application specific, like preamble, sync word, CRC, fields, and field sizes. For example, some devices may only respond if you have a certain start bit or certain preamble, certain order of bits which arrives at the receiver. Only then that receiver is going to take some action based on the transmission. Otherwise, not. So, which is a good thing. But it was never designed for security purposes. It was just for minimize the radio interference in general, which is always true. You always have radio interference. So cool. Finding the signal. So for the first step would be to identify the frequency and the bandwidth. A really straightforward way is to find out the FCC ID of the device if we have it. And you could just go on to fcc.io and you can quickly identify the frequency bandwidth and even the modulation type for some. Because if you have to operate, at least in the US, you have this requirement where you have to register and upload all these, the test data and all these schematics of RF-based systems, because these are going to be operated in unregulated space, like RF bands. So, but if we cannot, for example, this device I was trying to find out, I did not find the FCC ID, but I found the model number. And then, so there's a high likelihood of them operating in some of the ISM bands. It's not that hard. You're going to find out like it's within 300, sub 300 to 400 megahertz range. And if we are not able to do that, then that's what we have to find out. There are tools which help us do this exact thing. So there's a spectrum analyzer called GQRX. It's Linux-based, it's open source. It can also be used to record the signal. So it helps us visualize the radio spectrum. You can see in this image where it's represented as a. So this is all noise in this sense, whereas the red part is actually the signal. So on the top part, that graph is called the FTT plot, which is like the Fourier transform representation. But what really happens is Fourier transform is just when we actually receive a signal or something, the plot would go up in amplitude, and you can actually see that something was transmitted in that band. And then the lower form is the waterfall view, where it shows the received signal as a function of time. So that goes on as well. You can see that as a part of red flags. So as I said, this is available. Windows equivalent is SDR Shop. It's again this. So this is the RTLSDR hardware is actually going to tie into this. It's going to receive using that receiver. So this is pretty much open source. You can use Windows for that as well. There are other better alternatives in Spectrum and Universal Radio Hacker. They do pretty much the same thing, but they also go the extra step of they help you decode the signal as well, and actually help you convert to bits and bytes as well. Like it can actually show you what digital representation is being transmitted. And using that, depending on what type of attack you're trying to do, you can actually just replay or signal jam that particular frequency and stuff like that. So these are pretty handy. So for this purposes, I'm going to use Audacity for analyzing the signal. Audacity is basically was for representation of audio signals. But if you think about it, all RF signals are still in audio. You can play them. So if you open that up in Audacity, if you record it via GQRX and open the file in Audacity, you're going to see something like this. Now, if you get something like this, it doesn't make sense at all. So it's probably very noisy. So what we would want to do is to find out the exact frequency that device was operating. So if you have to capture the signal, for example, in this doorbell, you just click on the transmitter a few times, and you're going to see a waterfall model in the waterfall output for GQRX as to which actual frequency is being transmitted. So even if it says 315 megahertz, it's going to be operating, for example, in this one, it's like 314,895 kilohertz. In my case, it was a little bit over 315. So once you fine tune that GQRX to listen on that exact frequency, you're going to eliminate this noise. And when you eliminate that, you're probably going to see something like this. Now, this makes more sense because now you can actually identify whether the signal with power is going up or down. So yeah, this is just one of the waves. Transmitter typically sends like a lot of them when it does like one output. So this is like a very zoomed in version of the signal which I captured using that doorbell. So once we fine tune this, you're gonna get something like this. Now the main task for us would be to decode this into ones and zeros as to what would represent one, what would represent zero, and whether we can, is that a part of preamble or is the part of the data, and then we can go from there. So if you look at this now for replay attacks, we also have to figure out. Oh, by the way, we have to figure out the frequency, the modulation, and the type as well, of course. So what does this look like? So if you look at our previous slides, this is what an ASK modulation looked like. You see the similarity now? It's like literally the same, And then if you look further, this could be like on-off key as well, because the zero is represented by just nothing. It's basically the noise. And the ones are represented by higher power in the output there. So once we know that, our aim is to figure out, we literally have to generate this using our transmitter. And if we can generate that, you don't need the transmitter anymore. You could just replay it using our RF transceiver. So which is pretty interesting. So for decoding this, we'll have to figure out, depending on the width of these signals, as to what it might represent. So for example, over here, so this represents a 1. Now, if we think that this is 1, it might be 2 ones as well, but you don't know at this point. But at the same time, if we know the symbol rate as to, within, let's say 600 microseconds, I have to transmit a 1, and we adjust that baud rate over there, it will make sure that it doesn't matter. You just have to get that same waveform out there. It could be 2 ones, but if we could squeeze those in the same time frame, we will be able to reproduce this signal output. So for this purpose, I'm going to assume this is 1. But then if you look at the next, the down, the 0, basically, you're going to see the width is a little more. So you're going to assume that's like 2 zeros. And then after that, you're going to see in this, following the same pattern, you're going to see this is 1, this could be 0, that's double 1 because the width is like double of what we assume to be 1 over there, and so on and so forth. So if we follow this methodology, you're going to figure out that this is what it represents in this sense. Cool. So once we find that, so this is the binary representation of the final waveform. We get this to that. We're going to convert that to hex because that's what our transceiver understands. We can also transmit binaries, the same thing. So with that, once we have the representation of the digital signal in actual bits and bytes, we can tie the pieces together and see how we can actually pull up some attack. So RFCAT, before we actually start our dongle, the yardstick 1, which we're going to be using on this, it's based on Texas Instruments CC1111 based device. Basically, it's like a sub 1 gigahertz wireless system on chip. So what these guys from Great Scott Cat just did was like literally took that chip and created a fancy antenna for it so that it could transmit like a long range, and then created a whole device out of it. But the firmware is written, firmware for that is like RFCAT, which helps you control the wireless transceiver from basically a Python shell. So you could just write a program where you create an instance of this device, and you can control the attributes such as the frequency, the modulation, what do you want to transmit, stuff like that. So pretty much now you're controlling. It's based on the CAT program, on the Linux terminals. Basically, they made it like RF CAT, so that you're catting into the RF spectrum using this. So it's pretty simple to install. If you can install that, and you could check the RFCAT -R, and you could create an instance of RFCAT. You could do like ping, discover, debug, and transmit. So these are the methods which the firmware exposes for us to use, and we can use that to perform our attacks there. So if you look at our final program, what I was able to do, a bunch of imports. So this is just a Python program. We create an instance of RFCAT, and we set the frequency to the exact one, which I talked about using GQRX. So in this case, mine was like 315.039500 hertz. We set the modulation, which we identified as the ASK and OK. So these are predefined, and which the firmware actually supports. So there are a lot of them which it supports, which is pretty great. And then we set the symbol rate, the baud rate, which is the 4800. So you can actually figure that out manually, or you can actually get that from GQRX output as well, as to when you hit record, you actually know what the baud rate is. And that's about it. And so when we do like d.rf_exemit, so this is the hex string which we identified. We're going to pad that with a bunch of zeros, null bytes, and then send it, into this like 10 times, sending the same pattern, because you want to send that for redundancy purposes. And yeah, that's about it. So let me try. So because it's just a terminal program, I don't think there's anything to share, but I'll still, I hope you guys can hear the doorbell. And I'm just going to send, this is a Python script, and I'm just going to send the Python, run the program, and probably you guys going to get something. So there you see. So I just sent this whole script via Python, and this just freaking works. So what are the consequences? Nothing, this is just a prank thing. But there are other vulnerable devices which operate on the same principle, and those can have real consequences. For example, so the issue here is that there's no mutual authentication between the transmitter and receiver. So if there was something like that, even though there was like a preamble bit and CRC bit, but those can be easily forced, once you know one. So the most common ones are car key fobs. But those can be, so replay attacks like these are not that straightforward. Some of them, actually there are. The older ones, you can just simply do what I showed you, and you can just replay and the car would just open. So if anyone out there in the parking lot is there with a, a capturing device, they can get that. And once you're gone, they're going to replay and, steal your car or something like that. So the newer ones support something known as rolling keys. What it does is you can only use the code once. But then there are like still issues with that, because even though those codes are encrypted, you could still replay them if that code hasn't been reused. So if you for example, you jam that, you place a jammer near the car operating on that frequency, and you hit unlock, and then it's not going to unlock because the system is jammed, and then you unjam it, and you capture that rolling code, and you want to replay that from your own device and unlock, and you capture the next one because the person is going to, press this again because the card did not unlock, and you captured that for the time being, and you can replay that the next time it's done. So it's difficult in practice because you have to make sure that that code hasn't been used again, because only the last known code could be reused. So, but yeah, this is like a very valid attack based on the same principles which we discussed. Similarly, there are like garage door openers, security gates, all kind of access control systems, which basically operate on the same thing. You could capture it, you could jam it, you could replay, stuff like that. Yeah, as I discussed, like motion sensors, door alarm systems, everything. Yeah, and then there are a lot of proprietary non-consumer facing applications as well, which most of us don't even know about or don't even care about, but can have like very severe consequences based on where they are. It could be like a satellite or an airplane or stuff like that. So yeah, I think that's about it. I hope you enjoyed this and hopefully learned something from it. If you have any questions, this would be the time.
Well, thank you very much. I found this a very interesting presentation. It's always something I've been somewhat curious about. A couple of questions come to mind here. Most of what you were showing, I guess, was, for lack of a better phrase, an on-off thing. Are there situations where information like from your credit cards can be sent via those RFID, smart card sort of things?
So no, RFID and NFC. So those actually fall in the I think sub less than 300 megahertz, just like 125. But those are a little secure in the sense that your mobile application is going to do something. No. The answer is no, because straightforward. They follow a kind of challenge response protocol. However, if you can capture, you could still do a man-in-the-middle attack, as far as I'm aware. So, yeah.
Okay. The other thing I was sort of curious about is, do you know of any legislation or any, I guess maybe industry interest in securing some of this stuff, especially for things like, I'm going to hazard a guess, older, well, we used the car example, older vehicles and stuff, which don't necessarily have, weren't necessarily built with security in mind? Or is this sort of a thing like most IoT devices, which, they ignore security until there's an embarrassing breach, and then all of a sudden they want to do something about it?
Yeah, so it's pretty much the same, because so for consumer devices, even the car example is a consumer device. What happens is this is more like an AppSec problem, because this has nothing to do with radio, but the lack of authentication and authorization between two systems of communication. It's like as simple as stateless protocols like HTTP, where if you have the session key, you can pretty much impersonate someone. So for example, if I have the corresponding RF representation of some communication and that's not changing, I pretty much have access to your session. So as far as legislation goes, I'm just aware not transmit on these ranges. That's illegal. I think there's something called, you can become a ham radio operator or something like that. You can become licensed and do this kind of things. But for receiving, I don't think you can even enforce any kind of legislation here, because all you need is like a $25 device, which can just scanning all the RF-based systems. With respect to fixes, yeah, it all depends on the design. Yeah, the industry is pretty much following the IoT thing, where if something bad happens, we'll see about it. And that's about it. I hope that answers your question.
Yes, I think it does actually. That's kind of disconcerting to say the least that it's following the IoT pattern, because some of us at least would like to see the IoT pattern change, but that's a whole different discussion.
Yeah,
Um,
totally.
That's all the questions that I have at this point. So I guess I will thank you for your time. And like I said, it was a very interesting presentation. And I hope to see you all for our meeting on Thursday. And again, thank you very much for attending.
All right. Thank you.